Hey there, and here's the lesson on the binomial distribution, continued part 2. Okay, so just make sure you've got your calculator ready. So if you haven't got it ready, make sure to pause and go and grab it because you'll be using it a lot. Okay, so here's another example. We've got a fair coin is thrown 10 times. So the experiment's being repeated 10 times, which would mean n equals 10. Find the probability that 6 heads will occur. So we need to define what is a success. So in this case, it would make sense that a success is obtaining a head, in which case when you toss a coin, what's the probability that will land on heads? It's 1 out of 2. So we can define that. Let success be obtaining a head, and then probability of a success equals 1 over 2, because there's a 1 in 2 chance of it landing on heads instead of tails, and the number of experiments was 10. Now we also need to say let the random variable x be the number of heads obtained. So you can use this notation. X is binomially distributed. That's what this means. X is distributed binomially with n equals 10 and probability of success equals 1/2. So try to also think what would be the probability of a failure. It would be 1/2 as well, because it's 1 minus 1/2. Therefore, probability x equals r equals 10 CR. So using the n, we've got to work out what 10 CR is, either using the formula that I talked about earlier that's in the formula booklet, like n factorial over blah blah, or using the NCR function on the calculator. And then remember, it's like binomial distribution. You've got your binomial coefficient multiplied by the probability of a success, so p to the power of r, and then q to the power of 10 minus r, or n minus r. So using the same idea as before, so let's pop that in. Therefore, find the probability of there being 6 successes. So probability x equals 6 in this case will be 10c6, because r equals 6. So probability of success to the power of 6, probability of failure to the power of 4, and these two must add up to 10. Then you would work that out on the calculator. So you can use your GDC to work out 10c6. Let's just remember how to do that. So remember, you go, one way you can do it is you can go math. Now this is all to do with probability. So go across to probability, and NCR is right there. NCR, so you could just type in number 3 if you want. Oops. And then pop in the 10, pop in the, is it 6? Enter. There you go. So 210 is a binomial coefficient. So just reminding us how we do that. And so on. So here I've written 10, then go to math. I tend to go, in the old days we used to have to, go 10, then math, but you can cross that out if you want, because now you can just go math, probability, NCR, and then you enter in the 10 and the 6 then. In the old days we had to press 10 first. So nowadays it would still, so cross this one out, so it'd be math, probability, NCR, then you'd put in your 10 and your 6 in the appropriate spots, like I did, and press enter. And then you get the binomial coefficient equaling 210, which is just this part of it, and then you've got to multiply 210 by the rest. So if you do the calculator, you would do 210, you can do multiplied by 0.5, or you can put in 1/2, to the power of, what was it again, 6, and the probability of a failure, 0.5, to the, oops, delete. See what I did there? So I need to arrow across, yep, to open up the new one. 0.5 to the power of number of failures. There you go. That's where you get your 0.205 and so on. So write out the unrounded answer, and then you would write the rounded answer to 3 sig figs, which is 0.205. And that's a good little example. Let's do a different one. The probability that a particular page in a math book contains a misprint is 0.2, so 20% chance that there's a misprint. Find the probability that of the 12 pages in the book, 4 of them contain a misprint. So a misprint in this case would be the success. So we define the misprint. Let success be a misprint in this case. Even though misprint is a negative, it's probably easier to, because they've mentioned the fact that the misprint is 0.2, consider a misprint as a success. Then p equals 0.2. What would q be? That's right, q would be 1 minus 0.2, so q would be 0.8. And number of experiments is 12, because there was 12 pages in the book. And again, let the random variable x be the number of pages containing a misprint. So what this means is x is binomially distributed with n equals 12, so 12 experiments, and probability of success being 0.2. And then you can write this thing again. Probability x equals r is 12 CR, 0.2 to the power of r, 0.8 to the power of 12 minus r, like with binomial theorem. And then 4 of them contain a misprint in this case. So this is in general, and now 4 of them contain a misprint. So what does r equal? Let's write r equals 4 in this case. So probability x equals 4, because r equals 4, is 12C4, 0.2 to the 4, 0.8 to the 8, because 12 minus 4 is 8. And then you pop it in the calculator, of course, again, just reminding you how you do that. You go math, select, go across to probability. NCR is part 3, so we've got a 12, and we've got a 4 here. You could do that if you want, or you could work out that, maybe it's safer to work out that answer first, 495, and then times that answer by 495 multiplied by 0.2 to the power of 4, and then out of there, multiplied by 0.8 to the power of 12 minus 4 to the power of 8 equals, there you go. So that's the unrounded answer, and 1328 would be, to 3 sig figs would be this answer. So remember, always write the unrounded answer first, so make sure you do that too. And then part B, fewer than 2 of them contain a misprint. So less than 2 have a misprint. How could you write that? So probability that x is less than 2, fewer than 2, meaning that x is less than 2. As opposed to x equals 4, exactly 4 misprints, less than 2. When you think of that, that's going to be equal to the probability that there's no misprints plus the probability that there's 1 misprint. We don't add the probability that there's 2 misprints because it says fewer than 2. So it's not equal to 2. If I had an equal to sign, you'd have to have 0, 1, and 2. So you've got to separately work those out. Probability x equals 0 is 12C0. You can probably guess what that value equals. Let's write it equal 1. 0.2 to the 0, 0.8 to the 12 minus 0, and so on. 0.2 to the 1, 0.8 to the 12 minus 1. So you can feel free to write in a 1 there if you prefer. Plug that in the calculator, and what do you get? And you would end up getting the binomial coefficient will probably end up being 1, and so on. So for this one, because like Pascal's triangle, each row begins with 1. And you can probably also guess what this one would be. But if you're not sure, you can pop it in the calculator. Just remind you one more time, math. Make sure you're doing this yourself in the calculator because you'll remember it more if you do it yourself. Let's go back. Probability, NCR. So 12C1, what would that equal? Have a guess what you think it would equal. That's right, it's 12. 12C1 would be 12. 10C1 would be 10. 8C1 would be 8. Anything C0 will be 1 because it's like the first row of Pascal's triangle. I mean the first number in a row of Pascal's triangle. So that's what these two are separately, but remember to get fewer than 2, you've got to add them together. So therefore the probability x is less than 2 will equal this value plus that value, which is 0.275. Notice that they kind of went to more than 3 sig figs, so make sure you use the unrounded answers or else you'll get a rounding error in your final answer. Back to shooting Annie. So returning to Annie practicing her shooting, you know that from before the probability of successfully hitting a target was a quarter, same as earlier on. If the probability of Annie hitting a target is p and she attempts it n times, she would expect to hit the target n times p. So remember expectation from one of our earlier probability review topics. Expectation is the number of experiments times the probability. This leads to the generalization that for the mean of the binomial distribution, B and P, this means that out of every 4 attempts, Annie would expect to hit the target once because it's a 1 in 4 chance. So each time 4 hits, sorry, each 4, for every 4 times she shoots the gun, we would expect that she would hit the target once. She's got a 1 in 4 chance of success. In 8 attempts, you would expect to hit the target twice, because a quarter times 8 is 2, and so on. So for a binomial distribution where x is binomially distributed with NP, this means the mean value of x is given by NP. This is also the expected value. So this might ring a bell. It's the expected value of x. So if they ask it for the expected value, you would use that. Let's see this in action. An unbiased die is thrown 24 times. So what does n equal? That's right, n equals 24. Find the expected number of 3 shown. So what's the probability of getting a 3? So let success be defined as obtaining a 3. So in that case, p equals 1/6. And n is 24 because it happened 24 times. Same thing, let the random variable x be the number of 3's obtained. So x is binomially distributed with n equals 24 and p equals 1/6. The expected number of 3's is given by the mean, which is basically NP. So NP is 24 for n times 1/6. So 4 times. So we would expect 4 times. If she rolled the dice 24 times, we'd expect there to be 4 3's. The expected number of 3's is 4. That's pretty obvious, and it might seem so obvious to you, but you might be surprised how many times in an exam, if you're asked for the expected value, people forget what it means. This here's another example. So a bag contains 2 red counters and 3 green counters. So how many counters in total? That's right, there's 5. 2 counters are drawn at random from the bag without replacement. So we're not replacing this time. Find the probability that exactly 2 green counters are drawn. So that's important, it's without replacement. So probability of exactly 2 green would be 3/5 for the first. So you do the first one, probability of the first one being green is 3/5 because there's 3 green and 5 in total. And the probability that the second one is green is 2/4 because 1 green has been taken already. So that's why there's only 2 greens left in the bag, and it was without replacement. So there were only 4 counters left in the bag. So 3 times 2 over 5 times 4 would give you 6 over 20, which simplifies to 3/10. So that's easy. B, find the probability that out of 15 attempts of drawing 2 counters, replaced after each 2 drawn, more than 12 of them result in exactly 12 green counters being drawn. So try to define it in terms of a binomial kind of like lingo. Let's define a success as being choosing 2 green counters. So then probability of success is 3/10 because we've already worked that out. Probability of in one experiment of there being 2 green would be 3/10. What if you repeated this same experiment 12 times? So you picked a counter out, then picked a second counter out, recorded the result and returned it. Then you picked a counter out, picked a second counter out, recorded the result and returned it. And you did like that basically in total 12 times. Let the random variable x be the number of attempts in which 2 green counters are drawn. Then x is binomially distributed with n equals 15 because it happened 15 attempts, and 3/10 because it's a probability of a success. So therefore probability x equals r equals, find the probability that more than 12 of them. So what do they mean by that? So x equals r, so more than 12 of them, so x is greater than 12, meaning that there could be 13 attempts that are successful, 14 are successful, 15 attempts are successful. So because it's more than 12, not including 12. So you've got to separately work all those out, which is painful. So you've got to work out the binomial coefficient for 15C13, and so on, and then 15C. So you've got to separately work them all out. And then in the end, you'll get 8.72 times 10 to the minus 6. Pretty painful. C, what is the expected number of attempts in which exactly 2 green counters would be drawn? So now we're off to the expectation kind of question. So remember, expected number is NP. So there were 15 attempts in total, and the probability of success was 3/10. So the expected number of attempts in which exactly 2 green counters would be drawn would be NP, which is the number of experiments times the probability of success. We would expect 4.5 times there to be exactly 2 green counters drawn. So here are some GDC tips. So you can use your graphing calculator to do something different. So we can quickly calculate binomial probabilities using a graphing calculator. For example, to find the probability x equals r, as opposed to something like x is greater than or less than, we can use something called the binomial probability distribution function, which is Binomial Pdf. So how do we do this? Example. So to find probability x equals 2, as opposed to x is greater than 2 or less than 2, that kind of thing, for x is binomially distributed with number of experiments equals 10, probability of success equals 0.3, press this. Second vase distribution. So, whoops, just go to that. So you go second vase, see that opens up distribution. And it's not the normal distribution, we're talking about the binomial. So we need to look for binomial PDF is when it's equal to something here. So binomial PDF. It's going to be, you can't see, notice you can't see it here. So scroll up and then so you can see it, it's on the next screen. Binomial, is it C? There's binomial CDF and there's binomial PDF. So this is just probability distribution function for when it's x equals an exact value. As opposed to x is greater than or less than, in which case we'll use the cumulative distribution function. We're using PDF here, see PDF. So select PDF is what we need to do, so press enter on there. Number of trials is 10, see it prompts you, number of trials is 10. Probability of success is 0.3, 0.3. The x value is what is it equal to here. So x value is equal to 2. Pop that in and go paste. So here it just says, are you sure this is what you want? Yes, so you press enter one more time and that's our answer. So you would write it out unrounded. So see, it gives it to you there. So you could do it by hand, as we were saying, like, you know, using the NCR and all that kind of thing. This is a quick shortcut way to do it. So instead of using NCR, so for example, it would have been 10C2, 0.3 to the power of 2, and then 0.7 to the power of 10 minus 2, so 8. So instead we would do this, 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 and then you fill it in with those things, 10, 0.3, 2, and then it kind of just reminds you of doing that. That's it, unrounded. So to 3 sig figs, it approximately equals 0.233. So you use this PDF version, binomial PDF, when it's x equals an exact value. But what about when it's x is, to find probability x is greater than or equal to or less than or equal to something. For x is binomially distributed with n is 10, probability of success is 0.3 and so on. So ignore this stuff up here. So you would need to, because it's accumulation of a number of different probabilities added together. So by hand you would have to, if it was greater than, if x is greater than 5, or equal to 5, you'd have to work out the probability x equals 5, probability x equals 6, plus probability x equals 7, plus probability x equals 8, all the way to plus probability x equals 10. But that's painful to do, and so you could instead do it on the graphing calculator. Second vase distribution, let's get the calculator out again. So let's clear that one. Notice that one was PDF, but here it's an accumulation of a number of different probabilities added together. So you've got to use second vase, then go up to here. It's binomial CDF for cumulative. It's the accumulation of a number of different probabilities that accumulate. Whereas this one's when you've just got x equals a certain thing. Number of trials is still 10. Probability of success is still 0.3. And in terms of the x value, so in terms of the x value, you would just put in 5 in this case. So meaning up to what? 5, enter. I'm going to ask you, are you sure that's what you want? And so on, back to here. That's what we should get. So just pointing out that that's kind of like what we got. 0.952 is kind of roughly what we got. So here, yeah, and so on. So you can maybe just ignore that other one written down there. Probability x is less than or equal to 5 is approximately equal to 0.953. That's a shortcut to do it. Some calculator models, such as our TI-84 Plus, only allow you to calculate probability x is less than r. To find the probability if it was, so notice this, don't change it to this, it was x is less than or equal to r, so just leave it as it was. Sorry about the writing on there. But if, so here it was because I was in another class I was talking about if it was greater. So if they did want probability x is greater than, for those models it's easier to find the complement. So probability x is less than or equal to r minus 1. And then use the fact that it's 1 minus that value. So in this case, don't change it to this, just leave it as x was less than 5, because that's what it should be. X is less than or equal to 5 is what that example was for. Because that's what the default is for the calculator. Our calculator assumes that it's in the form of x is less than 5. X less than or equal to 5. Okay, so let's do one more little example. 72% of union members are in favour of a certain change to their conditions of employment. A random sample of 5 members is taken. Find the probability that exactly 3 members are in favour of the change in conditions. So it's probability x equals 3. So would you use binomial Pdf or binomial CDF? So it's not accumulation of a number of them. So it's going to be second vars binomial Pdf. So because accumulation is when it's a number of them added together. Oh dear, come back. Pdf. So same thing, we've got to put in number of trials is 5, because there's 5 members. Probability of success is 0.72, 0.72. The x value in this case is 3. And then go down to paste, enter, and then enter. And then we've got like 0.926, blah, 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 which rounds roughly to this one. There we go. 0.29 and so on. Find the probability that at least 3 members are in favour of the change condition. So at least 3 members, meaning 3 members plus 4 members plus 5 members. So probability x is greater than or equal to 3, and so on. So remember that with our calculator by default tends to do probability x is less than or equal to something. So probability x is greater than or equal to 3 is 1 minus a probability x is less than or equal to 2. So you would, because that's accumulation one, do you use binomial Pdf or binomial CDF? Let's see. So we go second vars, and it's binomial CDF because it's an accumulation of a number of them added together. Trials is 5. Probability of success is still 0.72. X value in the uppercase is going to be 2. Paste, what do you get? 0.137. So 1 minus that answer equals this amount here. So notice it was, you use 1 minus probability. If you want x is greater than or equal to 3, use 1 minus the probability x is less than or equal to 2. Because our calculator only finds it in the form of x is less than or equal to something. So that makes sense. The expected number of members in the sample that are in favour of the change. So expectation, remember, equals NP. So the number of trials times the probability of success. Oh, sorry, that was the answer. Here we go. Binomial CDF, blah, blah, 1 minus answer, that kind of thing. So expected value is N times P. N is, in this case, 5. Probability of success is 0.72. So 3 times 0.72 is 3.6 members. Okay, thank you for your patience with all that.